Morning, Bill.
Good morning.
I guess we're the only ones on so far.
So far, yes, haven't seen anybody yet, but it's a bit early yet. You still there?
Yeah, I'm still here. Can you see me?
Oh yeah, no problem.
Okay, good. I'm
Yeah, just
trying to recall how everything works here.
yeah. How's your internet connection these days?
Well, you tell me, how does it? I am using I'm using what's called T-Mobile, and it's much better than AT&T. Sometimes I
I
get
see.
some problems, but I think it's much better.
Well, I just recall that a few months back you had problems, intermittent problems.
I had lots of problems. What do you use up there?
It's a microwave link to like a what's called LTE. It's a it's local microwave connection to a tower, similar to cell phone, but it's dedicated for data.
Huh. Yeah, this is 5G by T-Mobile.
Yeah,
But it's
it's
internet. It is just a box. Everything is, the tower contacts the internet box that I have, and then it broadcasts it in the house.
so you don't need your cell phone or anything to be.
Yeah, you don't need wires or anything.
Yeah, well,
No,
that's
it's
good.
pretty good. It's pretty fast and pretty reliable. AT&T was, I don't know, it was always had trouble with that. Going back to our conference, the original conference, I so what's the weather up there? Getting cold yet?
That's that's no, it's actually pretty pleasant right now. It's getting cool enough at night that we most of the mosquitoes have gone, right?
Yeah, yeah.
Uh,
Yeah, we've noticed the mosquitoes here are very tiny now. They never used to be that way. They
yes,
used to be bigger. Now they're very
yeah,
tiny.
I'd say the same thing. Same thing has happened here, especially during the latter part of summer. We we said we had this wind from the south, and we said, well, now we're getting all those American mosquitoes.
Yeah, they're pretty
But I
pesky,
actually,
no doubt about it.
I remember them actually from being in the Caribbean, like in Barbados and so forth. Barbados had a lot of mosquitoes at night, but they were always so tiny you could barely see them. But if you did, they were little
And
black
they're fast.
dots,
They're
very
fast,
fast, very fast. Yeah.
high-tech
So
mosquitoes.
so maybe they evolved, or maybe global climate change or whatever. They're moving north.
God, just as the
But
coronavirus evolves too.
yes, I guess that's true. But as long as it gets, I know it's going to eventually get cold enough here that there won't be any anymore. So
Yeah, yeah, it's getting cooling down here too, actually. Have the leaves started to change on the trees?
just beginning. Yeah,
Oh,
it's
okay, ours hasn't started yet.
that's
Yeah,
another thing that seems to be getting later and later every year. Uh, we used to have frost in our garden like on anywhere first week in September, but now we seldom see that until November. Like we got an extra month of growing season, which is gives me time gives me time to cope with the extra chores this time of year.
I know what you're saying, that's for sure. Well, I had the wonderful experience of snow a couple of years ago, which was
Ah,
very unusual for South Carolina.
yes.
In Mexico, I saw snow was on the volcano peaks. but even those are
Mhm.
disappearing. We used to have glaciers on the volcanoes down near Mexico City, but they've disappeared, you know.
Yeah, when I was there uh, near the volcanoes, there was a city with the university there. Forget the name of it. It's a very nice university that was built on sort of partly on the campus of an old uh, factory of some sort. I think it was like a paper mill or something like that. And
Uh,
I
was that
forget
in
the name.
Mexico City or where
No,
was
it
it?
was about an maybe 2 or 3 hour drive from Mexico City towards the volcanoes. I I remember we could see the volcanoes in the distance, and
Oh, yeah, it might have been Chapingo or something like that. I haven't really been there, but yeah, you have to go over the mountains to get to Puebla. There's a
oh, I
pass.
see.
Uh, well, the original Passe de Cortez was between the volcanoes, the big ones, Iztaccíhuatl and Popocatépetl. That
Mhm.
but the road goes differently now.
Yeah. Okay.
Very
So,
historic.
what was the name of the last volcano you mentioned?
Uh, Popocatépetl. That's very
Yeah,
famous.
I won't
That's
even try to say it, but I think that was the one we could see in the distance.
yeah. It's very close to Mexico. On clear days, you can see it from Mexico City side, and in Puebla, you
Mhm.
can see it from Puebla, the other side of the volcano from Puebla.
I see.
Okay, we're getting Brian's come on.
There was still snow on the top of the volcanoes when I was there. That was probably 15 years ago. So,
Yeah, how many years ago was it when we were in Merida? Do you remember?
oh yeah, uh, yeah, it would be about that time. I'm not sure if it was the Merida trip or not. Um,
Yeah, I like that. That was a
well,
great meeting that that Zbyszek organized.
hmm. I used to combine sort of trips to meetings like that a lot, with extra time spent in with Zbigniew there, and sometimes I was staying at his place, and sometimes I was sort of on my own there. But we always spent a lot of time doing physics. In, no matter what the meeting was about, that was what I did with Zbyszek when I was there.
Well, that was one of my best meetings, actually. I thought it was really a great meeting down in Merida. I was very happy with that.
Mm. Yeah, yeah, I have good memories of it as well.
And of course, we had an
Hi,
opportunity.
everyone.
Oh, Brian's there.
Hi, hi, Professor.
Good morning, Brian.
Good morning.
So we're
Oh,
still waiting for Dr. Cruz.
yes, I expect he'll show up. He did not send me any emails, so I we can give him a bit more time, I guess. Thank you for sending that new draft um, of your paper, Dr. Sobchak. I admit I haven't had a chance really to look at it yet, but I'll sort of have it on my computer here while you're talking about it.
Yeah, I did just very recently. I discovered what I had been looking for that I hadn't got for but for what the last 6 weeks. I've been thinking about it.
Uh,
But anyway, okay, here Dr.
Good
Cruz.
morning.
Good morning. Sorry for the delay. I have some problems here with my Zoom, but now it's okay. Mhm. Okay.
Okay. All right. Excuse me. So today, I think our proposal was that the three of you would be giving shorter presentations of the same on the same subject. No, Brian was going to tell us something about quantum computers, I think. Did anyone have a preference as to how we should begin? I just mentioned that Dr. Sopcich had sent an updated draft of the paper. So if we could start with that, or Jesus, do you have?
I think we can start with the presentation of Professor Garrett and Brian. And at the end, maybe I can give my presentation.
You're just hoping that they use up all the time, and then you won't have to spend our.
Well, mine I can be pretty quick about it since I've been over most of the material already. I'll review some of it, but then I will I'll get to the main point that I hadn't been able to do before that I talked about.
Okay, sure. Well, let's do that and take it
Okay,
from
so
there.
I can start by sharing screen here. Hope I can do it all right. Okay, here it is. Okay, can you see that?
Yes, that looks
Yes.
Yes, Professor.
Okay, let's see if I can start here. So I'll go to the beginning. So I was able to write a pretty concise abstract. I might start with that, I suppose. Summarizes basically what now is in the paper. So maybe I'll just read it. In studying the unusual properties of a special Witt basis of a Clifford geometric algebra with Lorentz metric, a new concept of local duality makes it possible to define any real geometric algebra by complexifying this structure. Whereas a global basis of a Witt null vectors is defined in terms of a pair of correlated Grossman algebras in a geometric algebra of neutral signature. The special Witt basis of a Lorentz geometric algebra is defined in terms of a single Grossman algebra. The relationship between these different concepts of duality and their matrix representation is studied in terms of simple examples. In other words, I'm not going to go into many proofs, just trying to get the main idea but I think it's interesting. A surprising connection is exhibited between discrete Fourier and wavelet transforms and the concept of a local duality. Okay, so that's just something I came up with amazingly in the last couple of days. I saw that connection, and it seems very unusual, really. Okay, so I give an introduction, which is basically what I just said in the abstract, but with references included here. Well,
Just briefly,
so the whole idea is what I call local duality, and that's what I will concentrate on talking about.
For me, that's my first question when you even in your abstract is the notion of local duality. Like, in what sense can duality be a local concept?
Okay, so that's exactly what I'll explain by quickly going through the first section. Talks about that's what the purpose of this paper is to show you exactly what the relationship between these two concepts are. So first of all, I begin with global duality because that's the most direct connection to matrix representation of a so-called Clifford algebra of neutral signature, sometimes called the mother geometric algebra because it's so conveniently and easily represented by a matrix representation. So again, we've seen this before. Two nilpones are said to be anti-commutative if this is true. A1, A2 plus A2, A1 is equal to 0. Okay. A set of mutually said to be linear. Okay, well, that's nothing new. I won't. So that defines the Grossman algebra with the usual Grossman product of just A1 times A2 is a bivector and so on. A1 times A2, A3 is a trivector and so on. And they're anti-commutative. And now I pick a second basis, which I denote by B's, defining a second Grossman algebra. So it satisfies exactly the same ideas. And now this third, a pair of Grossman algebras defined by A1 up to AN. These are all null vectors, so they have square zero. We say that they're globally dual if they satisfy the additional property that AI Bj B plus Bj AI is equal to the delta function. So you can see that's kind of, if you think about Bj's as just being functionals of defining a function, it's exactly the definition of duality of, if you think about the Bj's generating the covector space and the AI is the standard geometric algebra, then you have two Grossman algebras, and but in this case, we're considering them to be in the same algebra. Well, they're globally dual to each other if they satisfy this property. In that case, we have theorem 1, a pair of globally dual Grossman algebras, G and A, and G and B form a Witt basis and generate the spectral basis of the geometric algebra of neutral signature, which is isomorphic to 2 to the n cross 2 to the n square matrix algebra, m 2 to the n, and so on. And now I'm just exploring defining a basis for this. And so you can see any geometric number in the simplest case where a dot b is equal to 1/2. I guess let's see. Well, yeah, AI, is equal to 1/2. That's right, because remember, 2 AI dot Bj is equal to the delta function. So that means that AI dot Bi is equal to 1/2. Well, considering that to be an inner product now on by finding the Clifford algebra with the inner product then. Okay, well, this is a way then of writing, in the simplest case, G of the geometric algebra of neutral signature 1, 1. Okay, that's the simplest. And you can see the standard basis, the matrix of the null vector is just 0, 0, 1, 0, B 0, 0, 1. BA is the idempotent, and then AB is the other idempotent defined by the diagonal 2 by 2 matrix. Okay, and now we define the standard basis generated by these two vectors A and B. Just E equal to A plus B, F equal to A minus B. And you'll find very easy to see that E squared must be equal to 1, and that's equal to minus F squared. And in fact, EF is equal to minus FE. They're anti-commutative. So that's called the standard basis of the geometric algebra G11. And they satisfy multiplication table 1. Okay, that's this table. Where is it? Right there. That you see there. That's the standard one we've seen many times already. I'm not going to dwell on that. Okay, so, and then of course, all I do in the next case is I just look at this, the second case. When n is equal to 2, then we can write the spectral basis for the algebra G22, the mother algebra of 2, 1, A1, A2, A1, A2. We put U1, U2. What is U1? Well, U1 is a product. B1, A1, U2 is a product. B2, A2. So remember, that's the Clifford product now. That's B1 dot A1 plus B1 wedge A1. And so that gives you the So that's the spectral basis, what I call the spectral basis of this mother geometric algebra. And we can write the geometric number G in terms of the two Grossman algebras, A1, A1, 2, that's a bivector. These are A1 and A2 are null vectors. And we have 1, B1, B2, B2, 1. Okay, that's the second Grossman algebra. And then we have U1 times U2. Well, that's an idempotent. And again, so if you look at this matrix representation, that's just well, there you have it here. U1 times U2 is 1. All the other elements is 0. So that the matrix representation for this idempotent, that's a principal idempotent, is just 1, and then everywhere else is 0. Okay, so that corresponds to the principal idempotent, U1 times U2. Okay, and now we get to the place of what I call, so we can compare it with this, what I call a locally self-dual Grossman algebra. Well, okay, a new possibility arises. So now I'm using different symbols for the nilpotents. Okay, instead of using A and B, because we've already assigned A and B's, we've already defined them. So I'm going to define new nilpotents, a new nilpotent algebra, which I call Cn+1 because it's defined by C1 up to Cn+1 be a set of linearly independent nilpotents satisfying the following two conditions. Okay, so they're linearly independent. Notice I'm using the wedge product now because I'm not saying, I haven't defined what I mean by the dot product of these two null vectors. I'm not, in the previous case, the dot product of any two distinct A1.A2 was equal to 0. AI.bj is equal to 0 for I not equal to j. But in this case, I'm only saying that under the wedge product, which is the anti-commutative, the usual anti-commutative product, that defines the Grossman algebra, which I call Cn+1 over a field, which we usually take to be real numbers or complex numbers, to the n+1 dimensional Grossman algebra with this wedge product now, not adjacent multiplication, that corresponds to the A1 times B1, A1 times AI times BJ are anti-commutative, but these are not anti-commutative now. Okay, now in addition, the null vectors in Cn+1 are said to be locally dual or quantitatively dual if for each distinct pair, Ci, Cj, and Cn+1, that Ci, Cj plus Cj, Ci is equal to 1, you see? Now, with the other bases that we had, that's different. Okay, here I'm trying to emphasize the difference. Notice that the property 9 of local duality is identical to global duality when I is equal to j in 7. Well, we can go back and look at 7 here. So remember, that's the relationship the AI and BJ had. For distinct I and j, AI bj plus b is equal to 0. Okay, it's only when I is equal to j that you have AI bi plus b I AI is equal to 1. But here, in this definition, Ci, Cj plus Cj, Ci is always, so any pair of distinct vectors or null vectors satisfy that relationship. So that is AB plus B, A is equal to 1 for each pair. So let A equal to A Ci, B equal to Cj, where I is not equal to j, and it satisfies this multiplication table 1. Where is it? There it is. So AI and BJ, Ci, Cj behave exactly. So let A equal to Ci, and B equal to CJ is exactly the same multiplication for any pair, any distinct pair of the single Grossman element that we have C1 up to Cn plus 1. So you can clearly understand there's a difference. We're talking about a different basis, a different type of duality. For any Ci distinct from Cj, I not equal to j, it satisfies that multiplication table. It doesn't matter what pair you pick. Okay, so that's the main idea there. Okay, the following theorem shows that the local compatibility algebra, Cn plus 1 is a special, what I call a special width basis for the geometric algebra G1n. Okay, that's the distinction then. Whereas for the global pair of correlated Grossman algebras, we had it generated a basis for the usual mother algebra, the geometric algebras of the form n comma n. This what I'm calling dual quantum duality or local duality. Any pair that this generates a specialized width basis for the geometric algebra of Lorentz signature 1 comma n. So when n is equal to 1, well, it reduces to the usual. It's just local duality and global duality are the same concept. But if you have more than one vector, then it's different. Null vector, it's different then. So what we're doing is we're looking at a specialized width basis of a local compatible Grossman algebra, which satisfies that new. And here's the theorem that governs its behavior. Theorem 2, the locally self-dual algebra, Cn plus 1 positive, F of the Grossman algebra, C wedge. Okay, that's just the standard Grossman algebra with the wedge product over the field F, which is I'm only taking to be real numbers and complex over the complex field. It provides a specialized width basis of the geometric algebra 1n, whereas E1 is equal to C1 plus C2, and F1 is equal to C1 minus C2. And for 2 less than or equal to k less than or equal to n, we have this definition. And that you've seen before. And now you've also seen this before as well. I'm not going to dwell on this because I think it's more interesting what I'm going to say about this. But so we have E1 equal to A1 plus B1 using these rules that we wrote down in 10 here. F1 is equal to A1 minus B1, C1 minus C2. F2 is equal to minus C2 plus C3. Remember now, C2 means it's just the sum, C1 plus C2. C3 is C1 plus C2 plus C3, and so on down the line. So right now I'm adapting the signature by using J. Notice that J is a standard. Oh, okay. Let J equal the square root of minus 1. So I'm not assigning any. I'm saying that is a real, the real imaginary number, which usually is denoted by I, but I reserve I for the pseudo-scalar of the geometric algebra. So I say J is just the square root of minus 1 as a scalar. It has no geometric interpretation. But it allows me to change the signature and convert, get a matrix representation of a Lorentz geometric algebra of Lorentz signature 1 comma n. Okay, so when I'm defining E1 equal to A1 plus B1, F1 equal to A1 minus B1, now remember C2 means minus C1 minus C2. Okay, now I'm changing the signature of that element by just multiplying it by, I'm changing my scalars to be J equal to square root of minus 1. So that means that J times F3 squared will have square plus 1. So I'm adjusting the signature of this by making it into an imaginary null vector. This, remember before I used to talk about positive or negative signatures, correlated null vectors where it could either be +1 or -1, but I eliminate that now. I don't use that anymore. I only use the positive signature. They're all positively correlated with inner product equal to 1/2. And then I get the negative signatures by just imaginary. It makes it much simpler, and you don't have to think about this. Remember, I used to have 2 multiplication tables where we had -AB, but I don't use that anymore. They're all positively correlated, which is why I use the positive sign here. They're all positively correlated. Okay, but now, okay, so that's just a way of looking at it in terms of this basis defined by this rule 10, which we've now looked at in detail. But now the interesting thing is the second idea that I had been puzzling about. Okay, it is interesting to note that the nilpotent C1 up to C4, defining C13 can be defined by, so this is a different basis then. Instead of using this rule 10, I'm using the new rule, E1 is equal to A1 plus B1. Well, that's C1 plus C2. That corresponds to the usual standard basis of G11. But now F1, oh, okay, I don't want to look at that. Let's look at this now. So E1, so it's just another way of representing this basis of the standard basis of the Lorentz geometric algebra. But this is what I really want to talk about. Okay, so we define E1 just equal to the sum of C1 plus C2 plus C3 plus C4, F1 equal to C1 with 2 minus signs plus C4, F2 is equal to, notice I'm just changing the order of the minus signs, F2 is equal to C1 minus C2 plus C2, 3 minus C4 divided by the square root of 2. So that's just adjusting it so that F1 squared is equal to -1 when you calculate this using the multiplication table that we saw, the local multiplication table for, okay, and then notice that the only difference is C1 plus, that defines the unit vector, which has plus square 1, and these have minus square. F1 squared is equal to -1, F2 squared is equal to -1, F3 squared is equal to -1. Well, you have to check those, but you can check it, it's true. More succinctly, you see I have this normalizing factor, so we can put that normalizing factor square root of 6E1, square root of 2 F1, and so on. And notice that the matrix becomes this: 1, 1, 1, 1, 1, minus 1, minus 1, 1, 1, 1, minus 1, minus 1, 1, minus 1, plus 1, minus 1. So that defines a new basis for the standard Lorentz geometric algebra, also called space-time algebra, also called the Dirac algebra, the Dirac matrices representing it, which I do talk about in the last section. But okay, this is what's really new here that I just realized in the last week or so, that if we define omega to be these matrices, 1, 1, 1, 1, 1, it's just the coefficient matrices, defining the standard basis from the what I call the local basis of locally dual null vectors. C1, C2. So they all have inner product equal to 1/2. C1 times C2 is equal to 1/2. C1 times C2 dot 3, C3 is equal to 1/2, and so on. That's different from the global duality that we talked about. Okay, but the interesting thing now is that I just realized in the last few days is that you can write this matrix gamma omega 4 by the lower dimensional gamma 2 and gamma 2 minus. Gamma 2 is equal to 1, 1, 1 minus 1. Gamma 2 minus, all I'm doing, I leave the first row the same, but then I change all the bottom. So you can see the relationship of gamma 4 to gamma 4 minus. I change the sign of all the elements below the top row. So we get 1, minus 1, minus 1. I change the sign of this to 1, plus 1, minus 1, plus 1. This one goes from 1, minus 1, minus 1, 1 to 1, 1, 1, minus 1, 1, 1, minus 1, goes to 1, minus 1, plus 1, plus 1. Very simple relationship, which is a new kind of a conjugation relationship. Namely, if I take a double conjugation of this thing, it reverts back to gamma 4. But notice that that allows me to write this matrix in terms of the lower dimensional ones. So here I define gamma 2 as 1, 1, 1, minus 1. Gamma 2 minus equal to 1, 1, minus 1, 1. All I'm doing is changing the sign of the second row then. Okay, and now we get the 8-dimensional. Well, that's the Lorentz geometric algebra G17. We have, well, with these normalization factors, 2f1, f1 squared equal to minus 1. All these f squared minus 1, e1 squared is equal to plus 1. But notice now I've decomposed this larger matrix, this 4x4 matrix, into.
Excuse me, Professor. Excuse me. But what is the matrix that you are using for get that product? Because it looks like a tensor product.
No,
Then,
it's
yes,
no.
No, yes.
This is just the usual matrix product. What I'm writing here. So
okay, I am trying to understand this like a tensor product.
No, that's right. I'm just using matrix multiplication at all times. So I'm using a matrix where the matrix can have geometric numbers as entries in the matrix. But here, these matrices only have plus and minus ones in them. But this basis, so just substitute gamma 2 in for gamma 2, and then take, again, you can see, look here, 1, 1, 1, minus 1. That's exactly gamma 2 repeated here, and then we have gamma 2 minus here, and then we have minus gamma 2. If you look at it, it works. And then this is just breaking this matrix into 4 parts, which are now gamma 4 and gamma 4 minus gamma 4 minus gamma 4 times. It's exactly this. It's just a representation of that, but breaking this up into sub matrices, 2x2 matrices. So that's what people do all the time with just matrix multiplication. I'm not using the tensor product at all. Yeah, okay. So now I'm getting the higher dimensional algebras. You can see, I'll come back to this simpler case in a second, but it's not quite ordered right, I suppose. But okay, so we normalize by these factors here. And again, you just multiply this. That's a 2x2 matrix, 2x2, 2x2, 2x2. So altogether, it's 8x8. Well, that's what converts the local dual basis into the standard basis of the Clifford algebra G17 up given at the top here. Okay, I guess you can see that. Okay, let's go down here. Okay, but the interesting thing now, if you take the determinant of this thing, you get minus 2 to the 12th power. Well, that's interesting. You have to, I worked for quite a while just to make sure that it was correct. And you can make I hypothesized that by arranging the pluses and minus signs, that this is the largest possible determinant you can arrange from a matrix consisting all of plus and minus ones. I believe that's the largest value, minus 4,096, and that's the same thing as 2 to the 12th power. And now, if we take E1 wedge E1 wedge F1 up to F7, we get minus 2 to the 4th over the square root of 7. And if we reduce this thing, okay, well, here I'm trying to generalize that. So if you take this, the more general case, the determinant of gamma to the omega to the 2 to the 4th power, you get this. Well, that's just, this first one is just the determinant of, okay, so the second one, this matrix here has determinant minus 16. This one has determinant minus 2. Okay, well, that's this one. Look, if you take the determinant of this matrix, you get 1 times minus 1 is minus 1, minus, that's minus 2, okay? If you take the determinant of this matrix, you get minus 16. If you take the determinant of this matrix, you get minus 4,096, which is minus 2 to the 12. And in particular, if you generalize that, you get these numbers, minus 2, that's 4 by 4, 2 by 2, 4 by 4, 16 by 16, 32 by 32. Have to be careful. But, okay, but now I just want to say, we're complexifying these things now, and that allows us to change the signature to get any geometric algebra GPQ, just as it's well known that any geometric algebra of neutral signature has a matrix representation in terms by changing the signature of the mother algebra. We can do the same thing to get a matrix representation of any Lorentz geometric algebra by changing the signatures of the standard basis of a Lorentz geometric algebra by making a row, one row or more rows equal to that. So here I'm just changing the second row to j minus j minus j, just multiplying the second row by j, and that gives you the geometric algebra, the mother geometric algebra, which has a standard geometric matrix algebra that we talked about before then. In this example, employing the Hermitian conjugation, again, if you look at this, it'll come out exact. So it allows you to reduce finding these determinants to, it's a new way of determining expansion as well, because we're reducing the expansion of a determinant to 2 by 2 matrices. And that's the idea. If you look at these equations, 15 and 18, let's just go by 15. So again, we're reducing this down. Remember now, each 2 to the k minus 1 can be reduced into 4 matrices, all the way down to 2 by 2 matrices. And that's the whole idea. But that's exactly what's done in discrete Fourier and wavelet transforms. If you look at these simple Wikipedia references, you'll find that these matrices that you see here are exactly what's used in defining wavelets and, well, a discrete finite Fourier transforms. So that's the interesting discovery I made just in the last few days, actually. The close connection of this local, well, this is a new determinant expansion as well. Like I say, usually people expand determinants by row or column expansions. Well, that's using the global basis. But for this one, you're expanding a determinant by using this strange 2 by 2 decomposition. And I believe that that's new. Well, maybe not entirely new. It's because it's very closely related to wavelet transforms, and in particular, discrete Fourier transforms. If you take a look at these Wikipedia references, you can see that, well, this is not really new. So, but this just gives an example, and I'm not going to go over this now because I'm exceeding my time as it is, but I think this is interesting to see how the complexification becomes a standard Dirac matrices in the Pauli matrices. That's referring back to space-time algebra, Hesnes' work, which is what got me interested back as a graduate student, what, 50, how many years ago in the 1960s? That's what, God, hate to remember how old I am now. But that's basically everything I have to say. I've worked on the references, so you can see these are the references in Wikipedia: discrete Fourier transforms, discrete wavelet transforms. So I will yield my time because I know that we agreed that I would leave time for the other two speakers today.
Okay. Thank you for that. It looks like you've made significant progress here.
Well, I think it's interesting that this last relationship to find a discrete Fourier transforms and wavelets. That fascinating. I looked at that a number of years ago. I didn't follow it through, but this actually relates it to Clifford algebras directly to the Lorentz geometric signatures, which I think is interesting.
I think that my question can be reformulated. If you can express that product that you showed before, like a Kronecker product, then
yeah, that's right.
Okay, that is the.
That's right. Yeah, I do that in a number of my papers. Yeah, but these products I'm giving here are well. That's right. Usually, I when I define the standard basis of the Grossman algebras, A1 and B1, A1 to AN, B1 to BN. That's right. I use the standard Kronecker product. But for this one, I'm using this new idea of breaking the determinant using a decomposition of a determinant by 2x2 matrices instead of the usual column row decomposition of a determinant. Have you ever seen such a thing like that? You determine a higher order determinant by breaking it into 2x2 matrices, which is, I think that's actually closely related to, like I say, discrete Fourier and wavelet transforms.
But I think that the question, Dr. Cruz's question, perhaps relates to the fact that you are using this block matrix structure so that the matrix product that you're talking about here, like in 20, for example, is not Kronecker product. I mean, it's a simple matrix product.
No, that's right. That's right. That's right.
But these are block matrices, so that you're thinking of the like the
the 2x2
matrix,
block matrices, because they all decompose into 2x2 blocks.
Yeah. So this
any determinant can be expanded by 2x2 blocks using this type of relationship.
So this is a 4x4 matrix times a column vector.
Yeah, that's right. Well, that's right. And that was
not a 2x2 matrix.
Yeah. Okay.
It's both a 2x2 matrix of block matrices, or it's
okay. But look at this. Look at this one. Gamma 2 to the k reduces to a gamma 2 to the k minus 1, 4x4 of that. Now you reduce each one of these, so you reduce everything down to a 2x2 block. Okay. It's a recursive relationship. So it defines it up and down the line. That's the difference between a local duality relationship and the global duality relationship, which reduces to the Kronecker product of what we used in the. Yeah, I didn't write that for the standard basis here. We can go back to that. Yeah, this is A1, A2. That can be written as a Kronecker product. This can be written as a Kronecker product. But I'm not using tensor products even in this spectral basis. People do that, but I'm only using matrix products and the Kronecker product to get the standard basis of the globally, the global duality, which corresponds to the usual vector covector. I think that's been missed, really. I think it's important. I think it's a very basic idea that people just got trapped by this usual definition of duality of vector space and the covector space and so on. But now I think this is a bona fide new definition of what I call local duality, defined by and well, this is the relationship, but it's a simple any two vectors. So well, think about this. It's just another basis of the Lorentz geometric algebra 1, n. And this is the first way I thought about that, a definition of that, of the standard basis of the Lorentz geometric algebra 1n but the more interesting one is which defines this local duality type property. Well, okay, that's so again, all you need to define multiplication is this multiplication table with that general with the C's. So we're not defining matrix multiplication in terms of row times column, which is very convenient for the mother algebra, defining the matrix representation of the mother algebra elements, which is basic for then finding the matrix representation of any geometric algebra. Well, you can do it equally well by local, just using that multiplication table for any pair of Ci and Cj. It has exactly the same multiplication table. So this defines matrix multiplication by a local, by just the product of any two elements in that of this basis elements. And that's different than the usual definition of duality, which is equivalent to vectors and covectors and so on. Well, I hope I've made that clear at least. So that's the interesting thing, which ties it to the idea of discrete Fourier transforms. And so notice that E1 is a sum of all of these things, whereas where I defined it up here, it was a much more complicated expression, which isn't necessary because, and this thing allows you to decompose, a new decomposition of determinants into 2x2 blocks. Again, no tensor product, which is natural only in the usual way of looking at things. But I think this is missed. And I would blame Cauchy and Cayley and those guys for passing over it too quickly and not recognizing this new concept, what I call, well, Clifford too, but Clifford, has a very good excuse. Unfortunately, he just died before he could continue his work, which is a tragedy, of course, which happens in mathematics pretty frequently, as Galois, of course, is a beautiful example of that. Okay, so anyway, so that's the idea which generalizes it. You just complexify any of these. So we keep this 1, 1, 1, 1, which corresponds to E1, and then these other ones define the relationship of the standard basis of 1n to of this null vector basis, which all have inner products equal to 1/2. Anyway, well.
Okay.
So I can show you the references again if you like. So these are, well, this is a nice general reference of Hitzer, Professor Hitzer, of all the new applications of geometric algebra in robotics and in all kinds of different areas of applied mathematics. I'm surprised it hasn't been, well, anyway, it's a good reference. And of course, the Lazenby group and in Cambridge University. Well, my reference is here. My new book here. Okay, well, these are preprints. These are the papers I mentioned. I consider this to be the fourth paper of a sequence of papers of calculus of compatible nilpotents, itinerant quantum integers, and the first one. Well, let's see here. Well, they're not probably all in the order they should. Oh, this paper is important, and that was this. Well, there's the ArchiveX reference to it. Okay, well, I can stop sharing if you like, so we can get on.
Thanks,
Okay.
Professor.
Thank you.
I guess it's my turn.
Yes, yeah, go ahead, Brian.
Yeah. Well, I'm gonna share. Um, where is it? Okay. Okay. Here. You can confirm if you can see the.
Now,
Okay.
Yes, that looks good.
I'm trying to put it full size. It's full size in your screen?
yes. No?
No?
Yeah, it is. It's good.
Okay.
Almost full size.
Okay. What it didn't let me. Okay. Now it's good. I'm gonna make a zoom.
Yeah, that's better.
to-
That's
That's
good.
Yeah.
that's good.
Yeah, better now.
Yeah. Yeah. Well, I took the kind of presentation that Bob Koch did in March 7 of this year to present like the basics ideas of CX calculus. As a background, when I started researching this area, it was started as an idea of applying category theory to quantum computing, or more generally to quantum mechanics, and it kind of transformed itself to kind of a set of rules that are inside of what is CX calculus to develop a better understanding and also make like the calculations when you are dealing with quantum computing paradigm easier. So um, it has been around a lot. Bob Koch and Alex Kisner, they are the two main representatives of this way of seeing or understanding quantum computing. But in recent years, it started to get more attention because it has like some insights that you cannot see on the first hand when you are dealing with Dirac notation or maybe with matrix products of the different circuits and gates that you use normally in quantum computing. So it has applications in the areas like circuit optimization, error correction, also what is called quantum NLP, natural language processing, and quantum machine learning. There's are like the main ones that you see nowadays coming with a lot of papers in those areas. But what I'm going to present is like the basics ideas of this theory, and it started with something that is called process theory, which is more close to category theory that CX calculus is, if you can say it that way. Basically, when you deal with process theories, you have like wires, which are like the types of information that you are dealing with, and boxes, which are the like a black box that does something, and you can understand that box as a process, as something that is happening there. So they have a like a really long book where they get all the details about how you can start with the process theory, and you can go to another type of or another part of this process theory, which is the linear maps, and how from the linear maps you end up with CX calculus when you are dealing well or applying these rules. So the first idea is this one. Uh, Inside this process, you have like a special kind of process, but those are also processes which are called states, which are processes that don't have input wires. They only have output wires, and also the effect process, which is kind of a process that doesn't have output wires and only has input wires. So that's the basics of the process theory. You have wires, you have process, and you have a special kind of processes, which are these two. They explain it as the state as we normally understand it in Dirac notation, and the state of a system. And the effect could be understood as a test or as a question that you get or make to that system or that state. So to make it more like easier, they present like how they transform their notation to Dirac notation. And here you can see in the front part, we have like the normal, in the left side, we have the state representation of a process theory. And we only rotate itself and we chop some parts of that like triangle, and we get like the normal Dirac notation of a get. Also, we can do the same for an effect, and we get the bra. And if we do like state and effect kind of a composition, we do the same process. We chop some corners of the triangles, and we get again the Dirac notation. They explain in the first book that they presented that this part is kind of a way of plan, or they explain that maybe the way we understand the quantum processes tend to live not in one dimension, but rather in two dimensions. So when you try to compress everything on a normal notation, you can get a lot of confused by making exponents or indices on the different variables that you are using. So maybe if you get more like a structure that is a 2D extension, you get more of the normal understanding of quantum mechanics. Another important thing that you have like is the tensor product that we also encounter in Dirac notation or matrix representation, where we get two wires. And if we see two wires, we understand that these two wires are tensor product between them. And also we can do that with the process. So that's only if you are like seeing these two boxes. We usually don't present them with the tensor product explicitly. we only put them together on the same level, and we need to understand that between them there is a tensor product. And finally, the last part of the basics idea of a process theory is the numbers. The numbers are basically when you apply an state and an effect, you get a number. And depending on the type of application that you are giving to your process theory, for example, in quantum mechanics, this could be a kind of amplitude, probability amplitude of a certain state of measuring that state. So you get these numbers, and you can play with these numbers in the process theory, and you can move around them, and it doesn't affect really how you understand the process that is going through. So you can play with the numbers, you can, and sometimes it's easier to not consider them only to the final part of the computation or the process that you are calculating. And that's one of the properties that these process theories have. So at the end, well, you get something like this in the general case, where you have a set of input wires and output wires, and these they can be connected with different process, and you also can have like states and effects, and you get a more complicated or more complex process that you are analyzing. This resembles me a lot of in computer science, when you are like explaining or studying a certain algorithm, and you can like make different diagrams to understand it, and it's really related to that idea. So from that, you start to give rules, and you ended up with a part that it's called, or an idea that is called um, linear maps, which is kind of the transition between the process theory and a matrix form, and how you can apply the rules that you have on matrix algebra, and you get the same results in the part of the representation as diagrams. So when you have that part, this is more like we are skipping that part, or the author of the original presentation skips that part because it's more tedious and it takes more time. But it's interesting because with the linear maps that you are generating, you can establish a theory that is compatible with the ideas of quantum mechanics, or the principles of quantum mechanics, without the need of Dirac notation or matrix representation. So you get another way to represent the principles of quantum mechanics without the need of, how do you say it? I think it's the Hilbert space, without the notion of the Hilbert space. So you can get a new kind of a way of understanding this part. The
So
first or the
no,
huh?
no algebra is coming in. You're not defining a multiplication in an algebra, or just a tensor product, or what? There's no multiplication in your diagrams here. Just everything is symbolic, I guess, right?
Yes, yes. The only kind of a product that is, it's the tensor product, because at the end, when you see these type of diagrams, you cannot understand them in terms of time, because you can transform them using different rules, and at the end you are only interested in the process and how this process affect a certain state. So you cannot have like for example another type of products there, because it could be misunderstood as a way of making a assumption of time, how you need to read these process diagrams. So at the end, one of the main ideas that they give you is that only connectivity matters. It's like when you see a graph. You have a graph, and you only concern about how this graph is connected. So The main product that is the most important one, it's tensor product. And if you want to translate this to like a normal notation, an equation notation, or a matrix form, you need to incorporate also like a composition product when you are getting like the steps of how, for example, this state H is applying or it's evolved by G, and how the results of the outputs of the state D and the process G came together with the process E and everything. So when you try to translate to another like mathematical notation or tool, you need to incorporate maybe a composition product or something.
How about,
Just
for example, the associative law? Can you say anything about the associative law in your pictures there, or that would be important translating it to an algebra or something?
yeah, as we see here, for example, we can interchange the order of the input cables and the process, and it's going to be the same. So this I'm in this paper, it doesn't have like a lot of the background because it's more like detailed and better explained also with the diagram representation and also like the mathematical form or the algebraic also matrix and the algebra form of these diagrams and how you can understand it. But there are a lot of rules that are implicit when you are talking with diagrams. So for example, as associativity, it's only changing like the order of how these processes are drawn in the blackboard. You can change it from one side to another, and you get the same idea as when you transform it to an algebraic notation. You get the same rules that you need to establish that process.
But Brian,
Mhm.
when you draw these diagrams, well, no, that one, perhaps the one at the bottom of the page right now is a good example where, no, the one where you had, can you
Uh,
just scroll it back? Yeah, bottom of page 3 there. No,
okay.
so when you draw that diagram, is that diagram representing inequality, like inequality between?
Yeah,
So you write
that
equal signs, right?
yes, and this is the special case when you have a number on your diagram that you can play with the number around. You can move it
Mhm.
around the diagram. You can leave it aside if it doesn't if you don't need it in your calculation. You can like put it aside, and after your calculation, you just only like put it inside again. So the numbers are like not really important in this theory.
But that wasn't my main point. I guess
Okay.
Dr. Sopcich was asking about, in what sense is this algebraic? Like, is this an algebra, right?
Yeah.
And so I recall from many discussions with Dr. Ushevich, Ushevich was especially interested in this type of diagrammatic language. So he referred generally to a kind of generalization of composition called grafting, which is the process of actually constructing or wiring the diagrams.
Yeah.
But an important aspect was that axioms like axioms of an algebra, such as associativity,
Yeah.
would be written as an equality, like so, but an equality in terms of diagrams. Right? So you would, for example, have a binary process with two inputs and one output, but you would wire that. So give yourself two of these boxes, one that has of the same type, but then you wire them in two different ways. So you take the output of one and put it the input of the other, And so that gives you like three different inputs and one output. All right. And
Yeah.
so you express the associativity law as showing that these two ways of wiring up these two boxes are
Mhm.
equal, right?
Yeah.
So that to me, when you start doing something like that, uh, that's where it becomes algebraic, right? In a sense, that's where. So the algebra is expressed in terms of these equalities of diagrams. Is that?
Yeah.
Maybe I can add a comment because when Professor Rosievica and I were working in Grassmann algebra, then we put this kind of relations in a graphical way, but that are expression of algebraic properties
Yes.
of this. Then,
Maybe
sorry.
continue. So continue, bro.
Yeah, and then maybe if you give it to me the opportunity of share my screen, I can show you the example of this kind of relations that we can
Yeah.
present here.
Yeah. And also, I had the same idea to share just a brief.
No, sorry, maybe at the end of your
Okay.
presentation, in the way we not disturb this. Okay,
Yes.
go ahead.
And I'm gonna show just a brief like representation of how we translate these diagrams to an equation. I'm gonna stop sharing this one. I'm gonna going to share another um, another window. Um, uh, this one. Okay. And you can confirm if you can see it.
Yes, we can see.
Yes, that's fine. Yeah.
Yeah. Like this is like the main idea of a process theory and how you can translate it through like a mathematical form. And there we have for example back here, this is the main book that they the first book that they released back, I think it was on 2017 or 18 if I can recall correctly. But this is like the way you can understand it on more on a mathematical way. So here is like all the development to establish like the properties you need to establish like a formal algebra. And I just wanted like point it out really quickly so it can like be more understandable. Yeah.
So it's like a grand an overall language that you can translate into different
Yeah.
ways. There's more than one translation, I suppose. It's a
Yeah.
super view of it from above.
Mm-hmm. If I may, I'm gonna show just briefly an example here. Everything is started because when you start to develop a new way of representing things, you get a lot of like I don't want to say like people tend to not believe on what you're saying, but how you can prove that what you're working it's good, right? So for example, here you have another idea of a process theory. So you have, for example, a quick sort as a process, and you have as an input type a list of numbers. As an output type, you have a list of numbers. This is like the general concept of a process theory, that you can play around with different stuff. It's not only subjected to numbers or to for example, in our case, qubits or quantum bits. It could be really anything. So the only thing you need to start considering is the rules you need to apply to these diagrams to be compatible with the theory that you are trying to represent it that way. Mm-hmm. So I'm gonna go back to this CX calculus presentation. If you have more questions, we can attend them right away, because I think it's in my case it also when I started to see this new like kind of paradigm of understanding things, it was really confused. But in the long book, they have a really good detailed step by step with all the mathematics behind it. But I just wanted to point it out, like the main idea of CX calculus, and not stop a lot in the details. Yep. You can see now the original presentation, the original PDF.
Yes, we
Okay.
we no.
Okay. So, well, as I was saying, you have the process theory. You started to apply these process theory rules, and you came along with something that is called linear maps. Linear maps is basically a way of transform these diagrams to a matrix notation. So you have all the rules that you have already known and well studied in matrix form are compatible with your diagrams. And this is the basics idea of transforming these linear maps into what it's called CX notation or CX calculus. The two main symbols that you have on CX calculus are going to be the C spiders and the X spiders. The C spiders are put it in green, and the X spiders are put it in red. There is no like reason that the authors did that. They usually tell the story about that when they were like developing the theory, they had a green marker and a red marker, and that's why they used to red and green. So, and in the case of the C spider, as we can see here, we have a n input wires and m output wires. In the same case with the red ones, every rule that we can apply to the green ones or to the red ones are compatible with one another. So that's a really important thing. It's kind of a symmetry between the two main symbols that we use on CX calculus. And how we transform this to a linear map, which is more typically studied on quantum computing, at least. We have this spider on the left, which is a basic C spider with n inputs and m outputs. And we can represent this as a linear map or in Dirac notation this way. So in all the development of this theory, we have translations between this form and the form of a CX calculus. We are going to see in just a few more pages why this, at least for quantum computing, which is the area that I'm researching, it's easier in certain cases to represent your circuits with these kind of spiders. And we're going to see it in a bit. Also, we have the same representation of a linear map for the case of the X spider, which is the red one. And we only take the plus and minus basis. That's the difference. And we have the same idea of n prime inputs and m prime outputs. In the case, we represent C basis as a standard computational basis in quantum computing, which is 0 and 1. and X basis is plus and minus. We started to see that applying these kind of spiders, we get different kind of rules that are the benefit of using this notation compared with dealing with quantum circuits using, for example, Dirac notation or matrix notation, that it could be really confusing ones. And some of these rules are also presented in Dirac notation or matrix notation, but are more complex to see right away. Like on first sight, it's more difficult to see these properties. One of the important ones could be the identity. For example, if we have like a Z spider, which is in this case with one input, one output, or the same could be for an X spider with one input, one output, and nothing connected between them, it can be understood just as a plain wire or something that it's not happening and not modifying these spiders. For the case of the Bell state and Bell state or bait cup, we can represent it this way. It only represents that the two wires are like passing or having the same state, which is the green spider, or it could be the red spider. And also, as we can see here, it doesn't matter if it's a Bell state represented on the X basis or on the C basis. At the end, in CX calculus, it would be treated as the same, which is only like a bended wire. And for the Bell effect, which is the measurement on the Bell basis, it only be an upside down form of this bended wire. Another important one could be the GHZ state. And also we represent it really easily with CX calculus, and we can like put it in this way, which is we have 3 wires, and all these wires are going to share like the same state that is going to be connected on the base of the wire, and also could be represented with the next basis, or applying like the identity rule and just remove it the green ball on the bottom. So what happened if we apply a phase to the spider? Well, we get a similar representation of the linear map, just adding, in this case, the phase to the states that are going to be affected for one of the basis states, which is going to be 1, part of the linear map. And we have this for the C spider and also for the X spider, which is the red one. So we have the same, just changing the basis. When we have the phase with us, when we have a 0 phase, we usually don't put it, because it would be the same as this exponent just to be 1, and we came back to the normal or first representation of a C spider or an X spider. How we represent gates in this case, for example, if we have a phase gate, which is a C rotation or a rotation in the C basis, we only apply or represent it as an alpha, which is the phase that we are applying to the wires. And in the case, if we want to represent, for example, a NOT gate, we could see that if we apply a pi rotation to this representation that we have here, we ended up with the same behavior as a NOT gate, usually very useful and well and used a lot in quantum circuits. So that's a representation. And finally, in the more complex case, how we see these CX diagrams. We see it in this way. You can draw it as you want. And here is the important concept that also I previously presented or mentioned, that it's only connectivity matters. It doesn't matter if you rotate your diagram or you change the position of these elements. You just only consider that the connections of the elements in this case the C and the X spiders, or the green and red spiders, are gonna be the same. If you are gonna change it, you only are gonna be concerned about the connections, and the connection need to be equal to have like different representations of the same diagram. In the case of the CNOT gate, well, we have like an interaction between a Z spider or green spider and a red spider, which is the X spider. So this is one of the more interesting ideas behind, because you can start seeing that the CNOT gate, it's an interaction between two bases, the C basis and the X basis. And in quantum computing, when you are dealing with the CNOT gate, most of the time they teach you a CNOT gate as a control gate, or as an if statement, seen from the computer science perspective, and it gets not the essence behind of what is really happening on your quantum circuit. But when you start to see in this kind of representations, you get more knowledge about how the CNOT gate is actually working. Because if, for example, if we have an state 0 coming from the bottom of the green spider, we get how this actually the CNOT gate works. Because if it's an state on the basis that it's in the case of the green one, with this part, which is the control part, the green spider, is not going to affect really the state. It's only going to pass it to the red spider, and the red spider is going to be responsible of changing if the condition of the state is correct. So that's only like a kind of parenthesis to see when you started to understand some important properties of the quantum circuits. And another important notion is that, well, these are the basis states and how you represent them. You have the C basis, which is the red, the 0 in red and pi in red, and also the X basis, which is the green 0 and the green with pi. It could be understood as 0, 1, or plus and minus. The universality, it comes from with the idea of the linear map. When they developed the theory about applying linear maps in these kind of notations, or use it as the background, mathematical background, to support these kind of notations, everything you can do on linear maps, you can do it on CX calculus representation. And since we have at least CNOT gates, C phase gates, and X phase gates, we get the universal set of gates we need to have to do any type of linear map representation. So they also give like a more profound proof and more detailed one of how this is accomplished. But this is important to notice that you have universality on CX notation. And also they prove this for qubits. And I think on August this year, they started to prove it for different elements like qubits and qubits in general. So it doesn't also, it not only applies to qubits, it could be applied to another more complex like elements. So we have like the unitary form. We put some states at the bottom. We process our unitary representation of CX calculus, and we get any state we want. And this is come from this idea of every process is, even the state is a process, so we can get any linear map we want to represent it. So basically that's when it comes to the universality. And the important stuff, which is the rules of CX calculus and why it's gained a lot of attention on recent years, is because you can apply these rules to your quantum circuits and make it more simpler, and also figure out different behavior that you cannot see when you have like a matrix representation. Because when you are dealing, for example, with 5 qubits, you get the matrix form that it's too big to really understand what is happening inside the matrix. And when you start like applying different gates, which are like this part of it could be single qubit gates or controlled qubit gates, this matrix or this process of multiplying the different matrix becomes too much um, complex, at least in my perspective, to really grasp what is happening on your quantum circuit or on your algorithm. So when you have these
I
rules, you
I'm
can.
just wondering whether this idea of local quantum basis would apply here. If you can represent this concept of global duality versus local duality, I think it's very
And
close to these ideas, actually.
yes, and this idea is gonna be here. Just to put it here is the idea of they call it on the main book, they call it when you have two types of complementarity in quantum basis. You have like normal complementarity, and you have also strong complementarity. And here is just a brief like insight, but as I mentioned before, if you want professors, I can send you like the main book, just to you can read it, some chapters to
Yeah,
maybe
please
match.
do. I would appreciate it.
Yeah.
It looks very compatible with the ideas that I'm talking about, really.
Yeah, and also for example, in this case, which is one of the most important rules that you have here. For example, you have a green spider, which is one basis, for example, the C basis, and the red spider, which is an X basis. And when you have two wires connected between those bases, you can cut it. You can cut the wires. Why is that? In the easy explanation, or from a physics perspective, it's like you trying to pass information between uh, position and momentum, and you cannot have that. So, for example, the red spider could be represented as momentum, and the green spider could be represented as position. So we cannot share information between each other, at least in this form. Everything here is like just the main rule applied, but it has the mathematical background to support it. So, but it's interesting to start to see this kind of a of behavior that you see from the physics perspective applied just to your uh, simple diagrams. And as uh, Professor Garrett said, we have like two important rules, which is the Hopf rule. It could be uh, at first sight to be very important, but there is a more stronger rule, which is the algebra rule. And this is when you get the strong complementarity. And for the specific case of a C basis and X basis, you have a strong complementarity. Not all the bases at least when you are studying quantum mechanics, not all the bases are gonna have a strong complementarity. Just certain bases are gonna have this property, and this property is out of my knowledge right now. I'm studying this part with more detail, but I just wanna mention that part, because when Professor Garrett start to talk about uh, the ideas that he's working on, I remember these properties that they mention on CX calculus, and I thought in that moment, maybe this is compatible. Maybe they share some properties between them, and it could be another way of proving that the path that Professor Garrett and this group in Oxford are following is correct. That you get the same properties and answers going from one side or from another side. So going back just briefly to see some of the basic rules, we have the fusion rule, which is a really easy one. If you have a connection between two green spiders, no matter if it's with or without face, you can put it together. So you ended up with a new spider that contains the information of both. You can also do that for the red spider, which is the X spider. This is like a really intuitive rule of just put it together with whatever is on the same color, you can put it together. So you have for example, an alpha face and a beta face of a CX spider. You just sum them together and you get a new spider, which is the sum of the faces of these green spiders. You get the same idea with the next spider. You also, when you have the fusion rule, you have to be able to go back, and that's when you came with they came with the idea of unfusing, which is only separate a wire that you are interested maybe on applying a certain rule that it's not clear at first sight, so you can like extract this wire from the previously fused spider, and you get like and you can also transform this to, for example, in this case, this could be seen as an output wire, but when we unfuse it and apply certain operations on the wire, we can now see it as an input. And that's why when you are dealing with CX calculus, you only care about the connectivity. You don't care about like the time flowing dependency of the spiders. And we go back again with the hop rule, which is and the hop rule or leg chopping rule, and the B-algebra rule, which is the square popping rule. So it only gets to separate like the different bases. And as I commented, it could be understood from a physics perspective, or also with the mathematical background that they developed to prove these rules. The other one, or the rule that I was talking about, that it's important or more important than the hop rule, is this one. When you have like,
No, I'm sorry. Mhm.
when you have, for example, a connection of this type of, as we can see it, of C bases connected with a certain pattern to an X basis, sharing this exact form, we can get a representation of this form. So this is important for us, at least for me in quantum computing, because you can start to compress your quantum circuit when it's really large, at least with the C0 gates, which are this part of here. You can understand it as a connection, a certain kind of connection between C0 gates. And it's really interesting because you started to get a more easy quantum circuit to deal with. So how this rule works, you have like this representation when you have a green spider, red spider, green spider, and red spider. And at the end, when you pass through these green dots and red dots between each other, you kind of disappear this square shape, and you only get with your result will be this new diagram representation, which is only gonna be the same connections or inputs and outputs from the wires, is gonna preserve them, but the spider associated with this connection is gonna change their color. So it's really interesting to see that, because what it's telling you is that when you pass through, at least in this form, which is a square form, you are kind of changing your basis or of your diagram. So the wires are going to be the same, the input and output are going to be the same, but the bases that are working, these wires, is going to be changed. So that's an important thing also to know. at least as I mentioned, for quantum computing is really important to know this stuff. So they also, Bob Koch also proved how you can get the hop rule, which is the first rule, the leg chopping rule, from the square popping. And this process demonstrates that this property of this B-algebra rule is more important than the hop rule. So you can develop like the demonstration using diagrams to get the idea of the hop rule, starting with this B-algebra rule and the unfused rule, and applying also the copy rule. And I just wanna put like a really quick example of how these rules are applied in a quantum circuit, just to see like the advantages that you will have, and maybe if it's continues the development on future research for quantum computing. In this case, on the left side, which is this part, we have a three qubit system. We are going to see it from bottom to top, which are connected with CNOT gates, which are these green and red dots. So we have, for example, a CNOT gate connected with from the qubit 1 to the qubit 2. Then we have a CNOT gate connected from the qubit 3 to the qubit 2, which is, we remember that the green dot is going to be the control. At least traditionally, we understand it that way. And we will have another CNOT gate connected from the qubit 1 to the qubit 2. So how when we see this in quantum circuits, we need to develop at least the Dirac notation and understand how these gates, these CNOT gates, are interacting with the starting state, which is normally is an state, for example, here 000 ket state, and how it evolves by applying these CNOT gates. In the case of CX calculus, we can apply the rules that we previously presented. The first one, which is the fusion rule, we can see that we can apply it here and here, because we have all red dots and we can fuse them together, and also green dots that can fuse together. So when we fuse it, it's important not to miss or disappear the connection that they have. So we have a fusion rule with the red ones, a fusion rule with the green ones, but we kept the two paths that they have. So when we have this one, we can apply the Hopf rule. So we can separate them. And in this case, this also, well, you get like a plain wire. When we apply the identity rule, is going to be as if we did nothing to the first qubit, and only the CNOT gate from the middle is the important part of the quantum circuit. And this is really interesting because at plain sight, you see that the circuit has like three stages. That you apply a CNOT from qubit 1 to qubit 2, then apply a CNOT gate from qubit 3 to qubit 2, and then again you apply a CNOT from qubit 1 to qubit 2. So you will think that it has three stages, when in reality, the first qubit, it doesn't get changed, and only the second and third qubit are the ones that have a process or a CNOT gate between them. So that's one of the important properties of CX calculator, that it gives you like ideas and knowledge of what is happening in your quantum circuit, and which parts of your quantum circuit maybe are not that important, or which parts of your circuit maybe you could optimize or erase or change. So that's pretty much it for my presentation. I think I took a little bit longer than I expected, but if you have questions, we can.
Hey, it seems to me like what you're developing is a Feynman diagram or quantum
Mhm.
mechanics, a way of picturing these quantum operations in a quantum computer, which is, of course, extremely valuable to
Yes.
help you one visualize what's going on.
Yes. Yeah, I think the idea that the authors have is to get a tool that it's more that gives you more intuitive rules
Exactly.
to understand what is happening, because
Yeah.
when you have a quantum circuit that it's not that complicated or not that big, it could be easier to understand it in certain cases with a normal notation like a matrix notation or Dirac notation. But when the things get complicated, you started to do operations on 30 by 30 matrices when it's not your computer maybe can do it, but if you want to do it maybe by hand, maybe you could take a lot of time to do it. So you started to lose knowledge and information about the process that are happening on your quantum circuit.
Yeah, I think that is exactly the strength of these Feynman diagrams that help people understand interactions of elementary particles in a concise way.
Mm-hmm.
Yeah, so it would be
And
very
also,
interesting to see how to represent this idea of local local compatibility and global compatibility of null vectors. Null vectors, of course, in idempotence are very important in expressing quantum mechanics, just as the Bragg and Dirac, Bra, and Ket operations are defined really in terms of idempotence and nilpotence.
mm-hmm. Yeah, and also I'm gonna send to you professors the main book that they presented, so you can like at least have a, if you are interested, a more um, uh, detailed explanation about the topics that I mentioned. I think it could be interesting, um, just to maybe
Very
put
interesting.
a kind of a final representation is how everything at the end in this book, they give you how you can understand at least the part of processes as different mathematical objects, as for example here an abstract tensor system, which are, I think there are some of the properties that they develop on CX calculus are also really close to the notation that I think it's Professor Penrose developed with for the, yeah, I think it's Professor Penrose that developed the contraction of tensors and ideas. So in this part, we have like a development of this, and also how it could be related to category theory. And specifically, the ones that we are that support CX calculus, I think it's a dagger symmetric special monoidal category. It's the type of category that they use as the mathematical structure, but just as a brief mention for that. I'm gonna send you this book, and you can read it if you're
Could
interested.
you send that paper to Basic CX Calculus for students and
Yeah,
professional?
yeah.
Yeah,
I'm gonna send both.
material there also.
Mm-hmm.
Yeah. Okay, well, that's great. Thank you very much, Brian. I know Dr. Cruz mentioned that he had the interest in presenting at least some part of what he was going to talk about today. Our time is limited though, so since we're coming up almost on 2 hours, but if we could if you could summarize it fairly briefly, Jesus, I'd be interested in
Okay,
that.
maybe I can summarize um, uh, I am going to share my okay. First of all, I was trying to fix the problem not the problem, the question about algebra. Then okay, I'm going to share my screen. One moment, please.
So far, my screen remains blank. Oh, here it is. Okay.
Okay, now you can see
Yes,
that.
I can see it now. Yes.
Okay. Then I wanted to put some definitions here about rings and modules, and then to arrive to the definition of algebras. But in the way of only to take the lower time, I only show this slide. And then here is in more detail the definition of algebra, like a set of three an array of three elements that are a ring, a field, and a morphism. And then I think that the question was directed to these morphisms here. Okay, I think that with the remark here, it is can be clarified because the ring R is a K algebra with respect to some phi. And this is the important thing because here phi is that the morphisms that get the representation of R in the using the K field, and then building an ideal for that. Then, if we use this kind of morphisms, then we get an ideal if of K, and then with that representation, we get one morphism to a subring of in the center of R. Then this is the paper of these morphisms. Arnold, that is the author that I am referring here, says that the custom is not to put these morphisms in the definition of algebra, and then only we used to put the ring and the field. But here it is important to emphasize the role of the morphines 5, because we want to use for the building of an interaction theory that can be based in different kind of morphines 5. Then this is the idea of put the definition of algebra in terms of this triad. This is one of the things that was that I wanted to prepare for today. And the other is in terms of the definition of interaction. I am going to use only this paragraph here, because this is the paper that I am preparing for the this subject. And here I wanted to discuss about the concept of the historical development of the concept of interactions. I need to add here some ideas of Newton and Leibniz first, but by now I have first the ideas of Trussell that discuss in a systematic way the continuum mechanics approach. And then in this approach, Trussell defines the principal concepts of interactions being bodies, motion, and force. It is similar to the way followed by Newton, that this started by the definition of mass, force, and quantity of motion. Then here Trussell followed the same way, but he defines these concepts related with continuum mechanics motion. And then he show in a systematical way how in a general presentation of motion, he can use in general two kinds of he don't use this word, but it's like two kind of universal laws, and those universal laws in the work of Trussell are the equation of continuity for the conservation of mass, the classical conservation of mass, and the equation of motion that I don't remember now. It was Cauchy that developed that general presentation of motion in terms of a generalization of a equation of motion for continuum mechanics. And following this, one can find the equation of Navier-Stokes in fluid mechanics, or the corresponding equations in elasticity theory. Okay. Sorry. Here I have the date was Euler, who formalized in this way the equation of motion for continuum mechanics. And after I aborded the problem of the concept of measurement presented by Franksen. And here the important thing that I want to discuss is how we can formalize in category theory the concept of measurement using two kinds of principal ideas that are the two dual kind of variables, two kinds of type of variables that are called transvariables and intervariables. And in another occasion, I presented to you like one point measurement and 2 point measurements that are the practical way of using this kind of variables to take measurements in one phenomena. Then this is the next step. And after I wanted to discuss some ideas of William Labert, that in some interesting papers, he discussed the idea of interactions. I don't remember, but maybe he don't use the word interaction, but discuss the category of two kind of objects and morphisms that are in natural process, that those are the space and quantity concepts that are dual. Then Labert expressed these two concepts like fundamental in the understanding of the formalization of natural of the theory around the natural process. And I think that as those are an interesting viewpoint. And finally, I arrived to the different ideas that worked with Professor Osiev about the interactions, but in that time we speak about observer, and for observer we work in the formalization of different parts of physical theories using two kinds of um, um, algebras that were related with one vector and a covector quantities. And then those give to us the different parts needed for build an algebra of servers. Then arriving in this with this idea, then we can start now with the formalization of the concept interactions. That part of this I present to you the session before. And finally, I wanted to apply this to different problems. For example, in classical mechanics, in electromagnetics, and maybe present some ideas in general relativity that Professor David David Antonio Perez presented in the past Congress in memoria of Professor Osiewicz. Then I am wanted to finish with those presentation and maybe some general ideas related with this kind of factorization that we can that we can see in this way of presenting the concepts of interaction, in where we have two kinds of morphisms here. One that is related with one point measurement, and one that is related with 2 points measurements. And with this, we can build the concept of interactions in this way. This is the general idea of that I am working in here, and maybe in the next session I can present this in more detail.
Okay. So I think you, based on your presentation or discussion 3 weeks ago, I think you seem to have a much more complete paper, and I look forward to seeing it in its entirety when you're done.
Yes, I'm sorry, I have not a version, a complete first version, but I am going to try to send to you before the session the next opportunity. Mm-hmm.
Okay. Well, I think that gives us an agenda for our next meeting in 3 weeks' time. Jesus, will you be able to give us the full version of this talk at that time in 3 weeks?
Yes, I need to um, put in order of this idea in the paper, and then I can send to you. I hope the next week maybe I can send to you a first version of this. Mhm.
Okay. I do have a couple of questions just from your quick summary, but I think I'd leave them till next time. But I'm very interested in your sort of justification for including the mapping in the algebra, like this mapping V. It seems perhaps fairly closely related to some ideas that are implicit in what Dr. Sobczak was doing. I think where we see scalar values appearing as elements of the Clifford algebra, for example, where the elements of the Clifford algebra, of course, are not actually scalars. They're actually elements of another formally they're elements of another algebra. So it's not part of the ring in a sense, right? But you do have a standard way of mapping the elements of the ring into Clifford elements. But maybe there are non-standard ways as well, and that's at least that's what I saw from that part of your.
It seems to me that there should be some relationship between what Brian was talking about and the pictorial representations that Dr. Cruz is talking about as well. I mean, they're both pictorial representations of ideas.
Maybe I can send to you but this is only an review, a brief review of the some ideas in the book of Anderson that is the rings and category of modules. Then is a brief presentation only of that ideas. But I think that we can try to go more deeper in this problem and think that it is an interesting way of getting different kind of representations of one ring in different fields using some morphemes for that. Then I think that is an interesting subject. If you want, I can send to you the review that I prepared for the presentation, and maybe this can serve to us for beginning a discussion around this. Mm-hmm.
Okay, that would be great. So I think in order everybody can continue with the other plans for their day, I think it's time that we should say it's the end of our meeting now and meet again in 3 weeks' time.
Okay.
Okay, professors.
Okay.
See you. Take care.
See you
All
next
very
week.
interesting. Thank you very much.
See you in 3 weeks. Yes.
Yeah, the same,
Okay.
the same.
Thank you, everyone.
Thank you.
Thank you.
Bye.